Hey guys, welcome back. Alright, let's talk compression. First question, why do we compress files? Simple answer, right? When you compress a file, you save space. And that is the main reason for compression. We all know Hadoop deals with big data sets, and obviously compression is going to save us a lot of space in our Hadoop cluster. That is the most obvious benefit. But there is also another less obvious benefit, but an important benefit. This is a good interview question. Compression certainly saves space. But what about the performance implication when you decide to compress files? That is, when you have a compressed file, you have to uncompress the file to process the data. Doesn't this add overhead to your processing and affect the execution times of your MapReduce jobs? Excellent question. This question was asked in an interview to one of our students. Him being the student of our course gave an excellent answer. This is where the less obvious benefit comes into picture. Nodes in our Hadoop cluster are highly active and they exchange a lot of data with each other over the network. And when you transfer compressed data over the network, there are two benefits. First, higher transfer rates. Since the files are compressed, you can transfer a lot of data in the same amount of time than you would do with uncompressed files. Second, compressed data reduces network congestion. So, when you have a lot of nodes working in parallel, avoiding network congestion by reducing I/O is not only important but essential and critical. So the overhead you would see in uncompressing the file is very minor. When you weigh in the obvious benefit, that is to avoid network congestion, which might affect the entire cluster. So there is no doubt compression will be very helpful in a Hadoop cluster. Before we look at how we can work with compressed files in Hadoop, let's talk about the types of available compression algorithms. There are several well-known compression algorithms: gzip, bzip2, snappy, etc. Faster compression usually means smaller space savings, and higher space savings usually means slower compression. And each algorithm has its own pros and cons. All algorithms exhibit a space-time trade-off. gzip is widely used and also sits in the middle of space-time trade-off. So let's use that for our experimentation. No matter what compression algorithm you decide to use, you need a piece of program called codec to compress and decompress data for each algorithm. Codec stands for compression decompression. Hadoop comes with codecs for several popular algorithms out of the box. For example, if you decide to use gzip for compression, you can use gzip codec class. If you decide to use snappy compression, you can use snappy codec. So now we know that compression certainly has benefits. Let's first look at where we can apply compression in MapReduce jobs. There are two obvious places compression can be applied. First, the input data set to the MapReduce job can be compressed. Second, the output data from the MapReduce job can be compressed. There is a third location compression can be applied, and it is the output from the mappers. That is, the key value pairs from each individual mappers can be compressed. This offers a huge benefit. Imagine you have a job with 1,000 mappers, and all the 1,000 mappers could potentially generate key value pairs. And this means that the key value pairs need to be shuffled and should reach the reducer over the network. And this would obviously result in network traffic. So when you compress the key value pairs coming out of each mapper, it certainly reduces the network congestion. No doubt, right? Okay. Now we know that compression can be applied to the input dataset, output dataset, and also to the key value pairs from the mappers. Let's now see compression in action. I have a dataset named stocks-big under this location right here, HIRW Workshop input file format. This stocks-big dataset is 1.2 GB in size. Now let's compress this dataset with gzip. To compress a dataset with gzip, all you have to do is just say gzip-c, the location of the dataset, and the final compressed dataset name. So let's copy this command and execute it right here. So the stocks-big dataset is being compressed now. The file is now compressed. Now let's look at the file. Okay, we see the file now. Let's look at the size of this compressed file now. So the compressed file is about 300 MB as compared to the uncompressed file, which is 1.2 GB, which is a significant space savings, right? Now, how can we use this data set in a MapReduce program? The data set that we have, that is stocks-big, it's a well-known data set for us. It is nothing but the stocks data set, which has day-by-day stocks information for various stocks. So here we have a MapReduce program to calculate the maximum closing price by symbol. Now, what do you have to do to let your MapReduce program know that the input data set is compressed? Nothing actually. Hadoop is smart. It looks at the extension of the data set. The extension of our data set is .gz. And Hadoop immediately realizes that the data set is compressed using gzip compression and will use the gzip codec to process the data set. Gzip codec is packaged with Hadoop distribution, so you don't have to do anything special, as long as the extension you specify maps back to what Hadoop can understand. Here is the compression format and the file name extension mapping. As long as you don't deviate from the mapping between the file extension and the compression format, Hadoop will have no problem dealing with the compressed dataset. Now that is for the compressed input dataset. Now how can we ask the MapReduce program to compress the output dataset? It's very simple. All you have to do is set two simple properties and you're done. In your command, where you're trying to execute the MapReduce program, simply set the value for two properties. The first property is MapReduce output file output format.compress equals 2. This enables the output dataset compression. That is, when the MapReduce job generates the output will be compressed. Next, you have to let Hadoop know what is the compression algorithm to use to compress the output dataset. And you specify that using this property, MapReduce.output file output format compression codec. Here, I'm using gzip codec. And this means my output dataset will be compressed by gzip. If you don't like to specify the properties here, alternatively, you can set these two functions right here, set compress output and set output compressor class in your driver program of your MapReduce job. The first function, set compress output, is set to true on the job, and the set output compressor class is set to gzip codec.class. Both functions are in file output format. But I like to set the properties by mentioning the properties in the command line because it is convenient, and later if you decide to disable compression or change the codec, you don't have to modify your MapReduce code. Just update the property here and you're done. Next, compressing map output. How can you enable that? Again, it only takes two properties. To enable, simply set MapReduce.map.output.compress equals true. And you have to specify the codec that should be used. You will use the property MapReduce map.output.compress.codec to set the value. And here again we are using gzip codec. Note the word map.output as opposed to just output between the output compression and the map output compression properties. So now let's execute this command and see compression in action. I've already copied the compressed dataset, that is stocks-compress.gz, which we compressed a little earlier, into this location right here, user HRW input file formats compression. And this is the output location, output file formats compression. So the output compressed dataset will be returned into this location. So let's first delete the output directory. Okay, there is no such directory, which is very good. I think we are all set to run the MapReduce program. There you go, the MapReduce job is now running. Let's wait for it to finish and then let's review the output. Okay, the MapReduce job is now complete. Before we review the job itself, let's look at the output. We want to make sure that the output data set is actually compressed. Let's do a HDFS listing on our output location. There you go, we see the data set. Let's now bring the data set to our local file system. We now have the file copied from HDFS to the local file system. Let's now unzip this file and then let's open the file just to see the output. Just to make sure that the output was generated fine. So to unzip this file, just say gzip-d, the file name. Your file should be now uncompressed. There you go, that's our file. So let's now open this file. And here's our result set. Okay, let's now move on to actually review the job. So here's the job that was executed. Let's click on it. Click on the history. As you can see, the job was succeeded, so no problems there. Let's look at the configuration and make sure that the compression values are set to the values that we are expecting to see. As you can see, the output.file output format.compress is set to true, and also the map.output is set to true and correctly to the codec that we are using, which is the gzip codec. Everything looks great. There is one small problem. Actually, it is a big problem. Can you see it? Look at the number of mappers. In our cluster, the block size is 128 MB. The size of the compressed input dataset is about 300 MB, which means there should have been 3 input splits, which should have resulted in 3 mappers. But the whole job was executed with just 1 mapper. This is very bad because the whole point of Hadoop is to distribute the processing of the dataset into many mappers so that we can achieve distributed computation. Why did this happen? Maybe the compressed file was stored in HDFS as just one giant block instead of 3 blocks as it's supposed to. Let's try the fsck command on the input dataset, which actually show how the input dataset is divided into blocks and into how many blocks and in which locations the blocks are stored. So let's try the fsck command on our input dataset. Running the fsck command would require sudo privileges, and you don't have sudo privileges in your cluster with your login. So you won't be able to execute this command. And this is how the command looks like. HDFS fsck, you give the input location. You say, I want to see the files under this location. I want to see the blocks for the files and also the location of the blocks. So let's copy this command. Let's execute it. There you go. The file that we are looking at, stocks-compress.gz, is split into 3 blocks as it's supposed to, and everything looks okay. So what is the problem? Why did the MapReduce job just use 1 mapper to execute a file which is 300 MB in size, which really had 3 blocks in HDFS? This is a problem with the compressed files because of the way compressed file is structured. When a file is compressed, the record reader in your input format cannot seamlessly position itself from one block to the next block. However, some compression formats like bzip2 allow splitting because it uses synchronization markers. An LZO compression format allows splitting when indexed. I know what you're thinking. You're thinking gzip compression cannot be used with Hadoop. No, do not come to that conclusion. There are file formats like sequence file which is inbuilt structure in place to overcome this technical difficulty and allow us to use compression format like gzip, which natively does not support splitting. We will see sequence file in the next lesson. So to summarize, in this lesson we looked at how compression can benefit us in Hadoop environment, both in terms of disk space and also in terms of network I/O, reducing network congestion. We also saw that compression can not only be enabled and used with input and output dataset, but also individual maps output can be compressed as well. We tried compression in a MapReduce program. Finally, we saw a major limitation with compression, which is the whole dataset was processed by one mapper instead of multiple mappers. In the next lesson, we'll see sequence files which offers a solution to this problem. With that, let's wrap this lesson. See you in the next lesson.